No. What is that? Can you repeat what is happening? And? No. $98,000, 2003. Yeah.
Or you would call you do you know my IP address?
Oh, hold a minute, I'm coming, there's too much noise here.
Too much. I can test it on I can test it on .52 if you want. Okay, perfect. Let's go there.
Good afternoon again with this second mobility session. The first one was oriented towards secure access to wireless LAN. Now we're going to look at a bit more frivolous uses of wireless LANs and also we're looking at ways of dealing with wireless LANs not always present. We have three very interesting speakers, I think. One of them is going to be a bit of a challenge because he's coming in via video conference from the States. But the video people around here have told me not to worry. In an hour they have figured everything out. So after the first two speakers, everything will work just perfect. So I'm just going to relax. Our first speaker is Dirk Kutscher. He works at the University of Bremen. And he is going to tell us about a very interesting project I think they are carrying out where they look at, basically what they're saying is you will never have always on, always connectivity, not even when you use wide area technologies like UMTS or GPRS, there will always be interruptions. So why not look at it from that perspective? Take the case where you have once in a while connectivity, perhaps sometimes a bit longer, sometimes a bit shorter. How are we going to adapt our applications, our systems to deal with that? Dirk, may I give the microphone to you?
Yeah, thank you, Klaas, for the nice summary.
I get it away?
No, that's fine. First of all, let me apologize for my croaky voice today. I somehow I caught a nasty flu, I guess, so I hope I can make it through the talk, but we'll see. Okay, let's get started. This talk, I'll take a somewhat different perspective on mobility than we usually do in the research community. I don't want to focus that much on techniques for optimizing mobility, for achieving seamlessness, but rather present an approach that we call disconnection-tolerant networking. That's one important element in one of our current research projects. As Klaas mentioned, we have a drive-through internet project where we try to provide internet access for mobile vehicles on the road by employing wireless LAN hotspots on the roadside, for example. Before I get to that, just let's have a look at the term seamless connectivity as we know it. So we all know different approaches of how to achieve seamless connectivity. Most important, there's the link layer approach. Today's second generation standard networks do that. In general, they are intended for wide coverage, ubiquitous connectivity, and their fundamental service is to offer a low bandwidth pipe with transparent mobility for the user. They are rather large cells. But if you seriously try to use that in cars or trains, for example, you always experience disruptions. So that's a typical phenomenon. Then there's, of course, the IP layer mobility approach, where the general idea is that I I maintain my IP reachability throughout my movements through the net, and mobile IP allows me to continue my ongoing sessions and to stay reachable all the time. And as we all know, there's lots of research work being undertaken for optimizing this approach. We have to do with handover delays. There's the vertical handover issue. There's whereas the basic approach is well understood, there's still some research and instrumentalization work to be done to make this really usable in real-world networks. And then maybe as an advancement of this, it's also being discussed for 4G generation. There's the hybrid approach where I could have a multi-home system or a system with multiple network interfaces and use them simultaneously and select dynamically which one to use for my current communication sessions. Though always best connected is a popular marketing term essentially. And while this is an interesting idea, still it does not provide any guarantee for seamlessness. So we still, of course, can have disruptions. And so essentially, seamless connectivity is it's a kind of a virtual goal that is really difficult to achieve completely. So you always experience service disruptions. You have to deal with battery life on your own end system. You have obstacles, just mountains, for example, and of course, the network can always impose problems. And while it might be technically possible to provide connectivity, you always have to. You also encounter economical problems. So it just doesn't make sense to provide GSM access in every village and every mountain valley. And even where you have, for example, GSM connectivity, sometimes it's not really that useful because the data rate might not be sufficient for your current application, and it may be for longer sessions, for example, be very expensive. And then there's also the case of nomadic usage that of course, is just cuts off your connectivity. If you switch your location and turn off your computer, your active connections are essentially disrupted or terminated, and you have to reinitiate them at a later stage. We all know the thing when going by aircraft that we have to switch off our devices. That's just one example. And one more comment on this. There are actually quite many applications that do not really need seamless connectivity. There are many applications that use short-time transactions, and they can deal with setting up the connections. For example, instant messaging programs or presence awareness systems can usually do that. So summarizing this, our approach here is that we say it's not that important, that effective actually to strive for ubiquitous connectivity, because you always have to deal with disruptions anyway. So our approach is to take back a step and to postulate the disconnection tolerant networking approach, where we say, okay, you have to take account of disconnections, and you have to make your transport protocols and your applications to be robust against that. So what do we mean by disconnection tolerant in detail? We all know some variant of this. If we as nomadic users, for example, we move around between our home office, our hotels, our conference venues, and so on. And we as users actually have learned how to manage these comparatively long periods of connectivity, because we are used to manually configuring our laptops, our wireless LAN cards, for example, and to resume our sessions, to reinitiate them. And this is something we already do today, because it's completely manual. It's, of course, rather cumbersome to handle. And but it's a way of dealing with disconnection and tolerant networking. Our drive-through approach that I will describe in a second is a rather extreme case for disconnection tolerant networking, because we really have quite rare and short connectivity periods where we have kind of bursty characteristics, and we have to be prepared for very long periods without any network access. And although this might maybe dissolve depending on the density of the access points, but in general we have to assume a very a very difficult environment, and in comparison to the first approach, where you are actually able to manage this manually, in this environment you really need to have support to manage your connectivity. So you want to have kind of infrastructure support there. So the goal for us is to actually conceal the intermittent nature of connectivity from the users, to, for example, to automate the connectivity establishment, and to support applications to make the most use of the very short periods of access. And yeah, this may be useful for vehicles on trains, but also just for the nomadic usage scenario when we just commute maybe on a day-by-day trip from our home to our office. So what does our drive-through approach look like? So we started off by saying, okay, let's look at a typical German autobahn, for example. There we have rest areas all over the place, and the typical distance, and the average distance maybe, is something about 5 kilometers. So if we just put wireless LAN access points there and provide them with internet access, how useful would it be to drive along with a car and try to utilize these areas of connectivity? It turns out that if you drive at a typical autobahn speed at 120 kilometers per hour, for example, the gaps between access points are quite small. Maybe 2 minutes or 3 minutes, and you can actually rely on the next rest area popping up quite soon. So what does it look like from an architecture perspective? So we have our wireless LAN-equipped car on the road, and we have access points and different service sets. We call those connectivity islands. And they have one or more or multiple access points per island. And then we have, of course, a kind of hotspot infrastructure that connects those access points to the internet. And we have servers that we might want to access from our car. So this is our basic scenario. And what we have done is to really try to how well does this perform in real life. So we have done some measurements, and it's just one example of a TCP measurement we did with a very basic Cisco 340 access points, no external antennas, and we did it with different speeds. And here we have correlated the TCP throughput against the distance measured from the first packet we received from the access point. So, and we can see that the maximum throughput is actually quite interesting. We can achieve data rates of 4 megabits per second for a considerable amount of time. And since we have done different experiments with UDP and TCP, we can also say that TCP is actually able to adapt quite well to the different throughput values you can actually achieve. And from our different measurements, we have obtained a kind of a typical process, a typical curve for the throughput. And we have an initial phase where you have unlimited connectivity, where you have lots of retransmissions on the link layer and a very low throughput, where you can not really do useful things. And we have we call it a production phase, where you can rely on having for 10 or 20 seconds really good connectivity. And then, of course, when you drive further away, it gets worse again. So this typical curve occurred in all of our measurements. And just to give an idea what you can really achieve with decent hardware, we have done some additional measurements with 11G hardware and high gain antenna. as compared to our previous 11B measurements, and that's really quite amazing. You can really get some significant amount of data through. If you look at the good put that you can really transmit in just different measurements, so the result here that you can actually transmit in a single drive-through session about 30 megabytes in 1 kilometer. Well, that's really can really be useful. So what this means for us is that we, of course, have to manage the usage of these connectivity zones. We have to concentrate the data exchange on the production phase. Just to make applications, make use of the high throughput phases, and also to not use up too much of the spectrum that would otherwise be used for retransmission and so on. So we have to concentrate our communication on the production phase. And of course, what has to be done is some form of auto-configuration and authentication. Wireless hotspots architecture have different approaches, as you all know. This has to be usable with minimal effort, and has to be automatic. And in general, our idea is to make these rather short-lived connectivity phases useful for applications. Our main approach is to provide a persistent transport across different connectivity islands. So our approach is that we maintain a transport session that persists the crossing of different wireless LAN islands. And the idea is that we will be able to exchange larger data volumes independent of the application. So, and another step we have to take is to provide application-specific support. Sometimes it's not sufficient to provide a transport-only solution, but you have to consider things like triggering applications, for example. When you enter a zone, applicants have to know when they can start their transactions, for example. In our paper, we have classified different applications and provided some taxonomy for that. There are the most important class of asynchronous applications like email, for example, or net news, where we have a store and forward principle. We have bidirectional push and pull, and we usually have the mobile node initiating sessions. And in those sessions, we have typically request-response-like transactions, and in most other cases, those transactions can really complete within one connectivity island. But those typical protocols like SMTP, for example, provide little support to recover interrupted transactions. So there is something left to be done. Access to web resources is quite similar. In general, it works, but you have to provide some support. There are applications that don't work that well. For example, interactive audio-video communication, where you have a continuous data stream, of course, that just cannot be made to work. If I'm out of reach of an access point zone, I simply cannot continue to communicate. There's nothing we can do about that. Then there's the whole class of a research track on its own for disconnected operations, for example, file systems like Coda, or protocols like WebDev and calendaring and so on. Those protocols are actually intended for disconnected operations, and they can be made to work quite easily. And of course, you can always think of new applications. For example, we are currently considering to develop a push-to-talk service where you just send messaging like voice samples in those periods. And that's also possible, of course. Okay, what have we done to support applications? This is, again, our drive-through scenario. And we have introduced two new corresponding components. The first one is a drive-through client on the mobile node, so a support function that can be in your car router or on your laptop or wherever, and a corresponding function in the network that we call the drive-through proxy. So these two provide the fundamental persistent transport service. And essentially, there are different levels of support that we can offer. First of all, okay, there's no support where we can just say, okay, sessions must complete within one window. You could at least provide some triggers that the applications know when to start their transactions. Then there is the persistent connection support I just mentioned, where essentially you conceal the intermittency from the applications. But you can go further. You can provide support on the application layer by doing transaction-oriented support functions in the drive-through proxy, for example. You can just have the proxy repeat transactions on behalf of the client. And you can even advance this. And, for example, for message transport, you can have local message stores and really do something like active prefetching, for example. We have looked at one particular application, that's email. As I said, it's doable in this environment. Sending email is particularly straightforward. We just have your drive-through client act as a local SMTP relay, and then just push out mails as soon as we have access again. But retrieving email, which we discuss now, is a bit more difficult. And there are different modes of accessing your email. There's offline mode, online mode, disconnected mode in IMAP4. And so let's just discuss this application by taking POP3 as a protocol example. Well, it's fairly simple, and it's still used by many email servers today. So just as a reminder, this is how POP3 works today. Okay. In essence, it's a request-response protocol with different phases, initial phases, phase of authorization, and we can request message lists and finally retrieve our messages. So quite simple. And now let's look how the different components behave for a POP3 session in this example. So we have our car here. Doesn't work anymore? Okay. We have our car moving from the left to the right and passing these different zones, and we have our four components. Our client that would be the application, our drive-through support function on the mobile node, and the drive-through proxy in the network, and the final server, our POP3 server in this case, and where the messages live. And we have, in this case, employed a message store at the drive-through proxy, and there are different. The design space in this case is quite large, so we have opted for a simple example, and so we have left out an additional variant where we could also have a message store at the drive-through client. So we enter the connectivity zone, and initially we of course have the phase of network attachment, where we associate to a wireless LAN. We do our IP auto configuration, DHCP or IPv6 stateless, whatever, and we have to authenticate using the concrete mechanism that is required here. And then we can actually initiate our application interaction. So the client initiates session through the local drive-through client and starts issuing POP3 transactions. So essentially, the fundamental model is that we have a careful transaction completion by the drive-through infrastructure. And in this case, we just assume that we can do the initial authorization phase end-to-end, and we send our credentials end-to-end to the server. The server has to verify that and sends an OK select back, and So we could go on. Unfortunately now our car leaves the first island and is out of reach. Our application doesn't know that and issues the next POP3 request, which cannot be completed, but the drive-through proxy in this case is actively prefetching the message in this case. This makes sense because in order to exploit the very short periods, you want to eliminate any delay that could occur, and the wide area transmission of your emails, the communication with the overloaded email server, POP3 server, could take some time. So in this case, we assume that we have a proactive prefetching, and this is being done here. And now we enter the next island again. And what we do is to repeat our outstanding requests and answer the local requests. So in this case, the UIDL request is being forwarded to the drive-through proxy and is answered. And this also triggers the client again to continue to go on with his POP3 session. So what it now does is just retrieving all the messages that have been locally have been cached by the drive-through proxy, and just continue with the session, without going end to end to the actual POP3 server. So this can be done, and we can, for example, now finalize the session if you assume that we just want to check email once, and terminate the application session, remove the application layer gateway state, and also terminate the drive-through session if we like, and are essentially done here. So this is just one particular example of how you could do that. There are myriads of other approaches, what you can do on the application layer, but just to give you an idea what forms of support might be useful in this context. So let me conclude. Essentially we have questioned the popular mantra of seamless connectivity. It's a useful term for thinking of optimizing mobility and so on. But in real life, you never have complete seamless connectivity. So you really have to deal with that, and even more, it's actually not always required. Okay, there are many existing transport protocols that assume that, but in effect, applications do not really need that. In our opinion, it's more worthwhile to just accept the fact that we need disconnection tolerant networking to take intermittent connectivity into account. And this may be viable for many, but not for all applications. We have seen interactive voice is difficult. Our approach here is to provide different levels of support by our infrastructure. And in particular, our drive-through approach, first of all, I think it's an interesting application in itself, but it's also quite a good testbed for this subject, disconnection tolerant networking, because it provides some very extreme characteristics. If we can make it work there, we can also make it work for nomadic use cases. And our approach is that we have our drive-through entities on the local system in the network to provide a persistent connection service, and in addition to provide application-specific functions as optional enhancements. So that brings me to the end. Thanks for your attention, and I'm happy to take any questions you might still have. Thanks.
I was just going to ask you to repeat the questions, but there the lady with the microphone has appeared. I think we have time for one question until we go to the next one. You're the first.
While the user is accessing their email, who is driving the vehicle?
Who is driving it? Good question. Essentially, we assume that we have a kind of a car router and multiple users in the car that do that. So you might have drive somebody else and just read your email and access the web, for example.
Okay. Thanks again.
Yeah, thank you.
One other thing about this, I forced Dirk to really cut down on his slides, but he also submitted a full paper which very clearly describes this whole process and also a number of other approaches. So please, if you're interested in this, read the paper, and I'm sure Dirk is available to answer all questions you may have. Now we are moving up a bit in the OC stack. It's a bit dangerous. We prefer to stay low, but I think we have a very interesting presentation to come up by Antonio Gomez Carmeta, who is Associate Professor of the University of Murcia, and he looked at another problem you might have when using all kinds of technologies, fixed, wireless, GPRS, UMTS, etc., when you want to combine it with demanding applications like video. He has developed an approach to automatically tune the video streams to the underlying network. I think I will stop at this because I don't want to take away anything from him, and I'm sure he's much better than me in explaining it. So over to you, Anton.
Okay, thanks, and all of you for being here. I think that this morning it was said that this session will be more esoteric than the first one. And indeed, in this case, it will be maybe the most esoteric one in that sense. So, the idea, basically, as you can see in the title, is that to present here some of the results we are obtaining actually in the use of different kind of techniques, basically artificial intelligence techniques in this case, as you will see, in order to try to improve what the user perceives in a multimedia session, in order to try to get more in touch with what the user really thinks is the quality of service in the multimedia application. So the idea has been to go one step further and not to only manage what we will say as network layer QoS, but also things that the user can perceive that it is better in order to improve his communication. And how we have integrated this in this case in the video, in audio and video conference application, and also in a test bed we have using ad hoc networks. So basically, the idea, what is driving the objective of this paper? Basically, the question here is that when you are working with in heterogeneous network, and basically when you are using multimedia applications, it is very difficult to try to solve everything at the network layer in order to decide exactly or to maintain a certain quality of service. In the sense that you can manage certain kind of parameters, but in several networks, think about ad hoc networks, think also, for example, in PLC networks, where it is very difficult to manage the QoS because there is high variability. For example, in the case of the PLC, for those of you that doesn't know it, the PLC is the power line communication. It's using the plugs in order to send IP packets. The problem there is, for example, is depend on the number of equipment that are plugged in a certain plug, will make a variation in the quality of the network you have in each instance. So to try to adapt and be able to manage a video conference there, it's very hard in some sense. So what we have tried is to see which are how we can cope with this heterogeneous framework. Not only just because of the network, but also, as you can see here in the slide, it's because also we must think about that every time we are having more different kind of terminals that are going to participate in the communication. And it's not the same to have a PDA connecting with a PC in the other side, etc. So you have to be able to manage different kind of configuration. Also, for example, just and using the example of the car, you can have in some moment a video conference using your laptop. You go inside the car and you want to transfer your session to the onboard computer that obviously will be not the same that the one you're having in your hand previously. So you must adapt the behavior of the application you are using. So this adaptation in some case obviously will be manage the QoS at the network layer, but in other case you also have to try to adapt the behavior of the application you have in order to try to maintain a certain quality from the user point of view. And this is what more or less we have tried to focus in this paper, to try to analyze how to adapt in this case and how to maintain a user perceived QoS in that case that must try to cope, as you have here, not only with network condition, but also violation of the QoS, for example, characteristics in some case, depending on the kind of the network, using different kind of resource and for the possibility of having a shortage, for example, CPU or memory in a specific device in certain moment of your session. And obviously, and this is, I think it's the most important things for next generation application is to take care about user preference. So always try to adapt also to what the user thinks is, from his point of view, more interesting. So just to show you basically what is the idea of, in this case, this slide try to, in some way, indicate that when you are trying to manage an application, a multimedia application, and maybe the variations that are being generated either by the network or, for example, because you are changing your device, that will maybe imply that you go from, in this case, from a picture or for a movie that is working with color. As you can see here, basically the main difference here is that we are changing from this picture, in fact, this video, to another one where the only things that have changed is the color. In one sense, you are using color, and in the other, no, in that sense. So this change, this adaptation of the application must be something that must be embedded inside the application. And the question is how and when we need to create this change. Which is the moment, which are the conditions, or what is the reason that create this possible change. So in some case, this change could be seen as the user saying that, okay, for me, it is more important to see a high quality, for example, a video or frame per second, but losing, for example, the color, because the color is not going to give me more quality in what I'm trying to perceive. Okay, this is basically the schema. So up to now, there have been different kind of work in the literature in order to cope with adaptive application. But in some cases, and normally they have to work with like a predefined combinations that the application can manage. So our idea has been to be more extend a little bit the architecture in order to be able to have different kind of configuration and also to work, as you will see, with several parameters that could be considered. So basically the idea, in some sense, is what was also shown here. At the end, from the user point of view, there is a no linear perception, in some sense, of the quality. It's not just saying, okay, because, as you can see here, the bandwidth is being reduced. It's not just taking, for example, less number of frames per second, or just reducing, for example, or changing just, for example, a codec. It's maybe the possibility is just, from the user point of view, is there is a relation or a certain combination that in certain point, for example, maybe his view of the quality implies that I have to change either, for example, the quantization, maybe changing in this case, to certain codecs, etc. But the idea is that it's not a clear linear behavior in what it is quality of service from the point of view of the application, especially when we're talking about a multimedia application. So many papers have just coped with this, the idea of that if bandwidth is being reduced, okay, let's reduce the number of frames per second. What we understand is this is not the solution. So we must try to describe and model what the user really wants or perceive as this a possible change that maintain in certain level the quality of the service from his point of view. Okay? So this is basically the idea of our approach. As maybe you have seen, if you have seen the paper, we have called it a user awareness quality of service. So we have tried to cope with the user perspective and try to describe, in some sense, what is his point of view. And basically the idea is not to just concentrate in low-level parameters, I will say, as bandwidth, packet loads, etc., and how we can manage in that situation. But also to try to be able to model, in some sense, or at least to try to do it, what is the combination of the parameters from that better adapt or better reflect the perception of the user, and trying to cope as much as possible with different kind of parameters that can be involved in all the process. So in order to do that, we have worked basically in two directions. One of them is to try to define, in this case, an architecture for the multimedia adaptive application, as you can see here, that try to cope with this possibility of changing the conditions and the parameters of the communication. As you can see here, basically we have three main models. One is the one that cope with the interface with the different kind of multimedia components. It's audio codec, video codec, frame rate, size, quantization, etc. So the aspect of the communication that we of the multimedia that we can be able to modify and to change during the process, during all the communication. Basically, the idea here is just a small snapshot of it. Basically, actually, what the multimedia application using zip initially negotiate with the other end user, which are the combinations or which are the possibilities they have. So they make an initial agreement about the possible change, the codecs, for example, they can use. And then during the process of the communication, depend on certain operations, in this case, what is called the adaptation logic, this can be changed dynamically during the session. Okay? So, for one side, we have the possibility that inside the adaptive application, we can change it dynamically, all these parameters. And in the other, there's two important models. One is about the QoS signaling. The idea is that we need certain feedback about how the communication is being done, what is happening, what is, if there's certain kind of losses, if there are some delay, etc. Obviously, in order to manage, this will be the more network-like components. And so all this information is going to help also in the process of making the change in the adaptation. And the other component is what we call it adaptation logic. The adaptation logic is the component that we will show afterward, that we have used specific algorithms in order to try to characterize which are the possible combinations that better adapt to the user perception of the quality of service. Okay? Learning using, in this case, a collection of data we have gathered in different experiments we have done. So the idea is that also the QoS signaling here has also helped us in order to collect different kind of information about different situations that are to be considered, etc. That then is complemented with the user perception. Okay, so just in a simple, very simple way, the idea of the adaptation, the part that is more classical, I would say, is the one that takes care about when, basically it's the two important issues here, these two final components, when we produce a change in the characteristic of the multimedia. When we change the components, when we increase or decrease the size, the color, or the frame per second, etc. So basically this process is launched, in this case, by the information we receive from the status of the communication, what is called the QoS report. So depend on, basically what we have done is in some case using RSTCP and in other one using a specific QoS signaling, what we've done is collect this information, and when we see, for example, that the number of reports are lost over a certain threshold, then we start the process of, for example, downgrading the quality of the multimedia session. Okay, and in the other case, when we generate the process control. So the idea, as you will see also then in the testbed, is that you are able to use the application in different conditions of the network to change from one kind of network to the other, and always you are aware about different situations, different change, and this change launches the process of adaptation inside the application. Okay, so basically here the problem is there's a lot of different parameters you can consider in order to cope with the quality of service. Okay, as you can see here, basically this is some of the ones that we have been working: audio and video codecs, video quantization factor, audio sampling, video frame rate, video size, component selection, buffering, etc., etc., etc. So the problem here is that, and many papers in the literature, what they decide is to take 1, 2, or 3 of these parameters, they make some tests, they say, okay, they create their own decision model, and okay, that's why, that's how my application is going to work. So the problem here is that, okay, it is important to consider also from the point of view of the user, and also not from one user, but also from a group of users, and because it is gathering information from different users, is which are the combinations that are preferred in the sense by the user. Why? Or why is the reason, for example, that in the other example is the user decide to see a video in black and white instead of color, because in that way he preferred to have a more detailed information about what is happening, and maintaining in that case from what he's called the quality of service. So the selection of these parameters is not a simple solution. So how and when we are going to generate the possible transition? So from our point of view, and this is the second part of our work, has been to try to be able to cope with this is the user, what is the user perception of the quality of service, to try to gather all this information. In that sense, this is not really new. The ITU, for example, has a specific, for example, classifiers of voice quality using some tests that are called the MOS, that just do that. Try to analyze how is the quality of the voice communication, and they characterize the way that and it is a user guide process. Okay, it's not someone that say, okay, this is a better combination. This is just a process that the user can define. Okay, so in order to try to cope with this user awareness, how to detect it, what we have tried here is to apply results, in this case of the artificial intelligence, specifically from machine learning techniques, in order to try to model basically the behavior of the user. One of the issues here is that, okay, it's very difficult, it's not clear how a user is behaving, so let's think about a black box. So a typical identifier of the system, where we will have a black box there. The black box will be a collection of data where the user can indicate his perception of the quality of service of this different combination, and try to extract from this black box using, in this case, an inductive rule generation tool, extract the rules. So then this rule will be part of the adaptation model that we have just indicated in the architecture. Basically, the idea is that we're not going to work with one user, but a collection of users in different conditions, and try to extract from these different conditions to try to obtain a model about their own perception. Okay, so this is what basically we have done in this case. We have used a rule induction technique. In this case, it's called Sleeper. Basically, what we have done is create a testbed where we can work with several kind of parameters, as you can see here in the left side, about bandwidth, different bandwidth. Different codecs for audio, for video, frame size, quantization, frame per second, percentage of loss. Also, we have generated a network condition, typical network condition, or a broad broad scenarios of different network conditions. And for all these different tests, the user finally, and the user put there, and normally we have used not an expert, or okay, I would say, communication people. Basically, we have used a student, for example, and also people from other areas, in order to classify, to put a score about what they think about what they are seeing in that moment. And in different conditions, okay, they score from 1 to 5 according to the ITU classification, in order to clarify what is their point of view, the quality of what they are perceiving. Okay, so using this, we generate a collection of data, as you can see here, data set in different conditions. We also have another group of data that have been used as this for training, another one for testing, and then we apply for this collection of data a sleeper algorithm. Okay, so the sleeper algorithm, as you will see, generate collection of rules. These rules will the sleeper algorithm, it is managed by a parameter is called T. T is going to depend on the value of T. You can have more number of rules, and obviously more complexity of the model, or less number of rules. Okay, so, and as you will see, we try to get a point where we have enough quality in the results, enough performance in the results, and and these rules are the ones that are going to go to our adaptation model, okay, and will represent the user perceived. So here is as you can see here in the figure is the difference between depending on the number of t, on the value of t, in this case, between the classification error. Yes, we have data for the training and then data for the testing, and the complexity of the model that is in this case indicated by the number of rules you can have. Obviously, having a lot of rules, we will have, as you can see here, high performance or high quality of the classification, but obviously it were more difficult to be managed inside the classification. So we have to arrive to an equilibrium between both. No? So we have to choose, as you can see here, t equal 5 in order to obtain a very acceptable performance in the system. So from this collection, specific collection of data, as you can see here in the left side, more or less some summary of the results. It is clearly, for example, that in the case of high quality of service, or what they understand is high quality or better quality, is the frame rate. It seems it's not as important, for example, as it will see. They prefer, in this case, that the video could be higher, for example. No? This is the kind of conclusion. Also, for example, in the case of audio, it seems that the PCM, in all the cases, was not necessary, not very important from the user point of view, and etc. Okay, so as you will see. So basically, just to give you a picture of, maybe obviously, either me, I cannot. I have to go in detail. I'm not going to go in detail in each of these rules, but this is the kind of rules we obtain. No? For example, the first one is if the quantization factor of the video is upper 60 and the video codec is MGPEG, etc., etc., then we obtain a value in this case, and depending on this value, finally we decide from 1 to 7 which is the most quality we can classify this condition. So what is going to reflect this from the point of view of the adaptation model is that if in certain conditions we will have to match the left-hand side of the rules in order to detect if we are in this case. And if we are in this case, we go to decide certain combination, in this case, of parameters. So in order to check all this, we have created a testbed using a specific, in this case, a scenario where there will be a high variability in the condition of the network, and it is an ad hoc network created on the basement of our faculty. Here you can see the different access points where it is based in using, in this case, access point, where we have implemented a multimedia, a multicast protocol that we have also developed. This is the MMR-RP. It's for ad hoc networks. So, and in order to test it, we have managed application. It's called Isabel Lite. It is a light version of the Isabel that maybe some of you know, that developed from the University Polytechnic of Madrid. This is a small application that is able to change in real time the different condition of the parameters as I have just indicated. Okay, and the idea here has been that the user goes from the S point, the source, to the final destination, that is the R point, going through all this basement, and obviously during this process he will have different kind of condition. For example, depending on the number of walls he has to traverse the signal. Also, there are some points obviously with overlaps, etc. So it was a very good scenario where to test a high variability condition in the application. So just to also give you a picture, basic on of the rules that have just indicated, what we create was a collection of different scenarios, in that sense, or steps that depend on the different conditions, as you can see here, of the networks or on the bandwidth available. We can make a specific selection of the codecs of audio, video, rates, and etc. And size, for example, from the video, in the case of the video. So the idea was to show exactly this kind of behavior. And here, now just the results. This graph represents, for example, and clearly indicate how the adaptation application outperforms the one with no adaptation. As you can see here, during the time, this is the time of the walk from the S point to the R point. and where, as I have indicated you, there are different conditions in all the traffic. As you can see here, either in the audio and the video, it is the number of loss. Also remember that because we are changing the parameters, also we change the traffic and the need of the traffic, so also we improve, in that case, the total loss that we are having because of the congestion and the problems in the variability in the strength of the signal, etc. So in both cases, it is clearly an advantage of the adaptative application in case of the non-adaptive. And also, as you can see here, the behavior is rather stable. It's not a straight line, but more or less, as you can see here, these are both are adaptive one. Clearly, they have a very stable behavior in the different conditions that are happening. Okay. This is just it's an histogram of the audio and video loss rate. In that case, as you can see here, the difference obviously this corresponds with the adaptative and the adaptative. In each case, more or less, 90% of the time we obtain less than, in this case, 5 or 7% of the loss. So it is very good behavior from the point of view of the application. So we maintain the quality from the point of view of the user. But this could be more from a classical network quality of service, because we are just measuring the quality of service of loose parameter packets, in some sense, from the network. What is important, and this is the main results I will say, is what the user said about the behavior during all this process. Okay? And here you can obtain, here are the score using the MOS classification of the user during the whole process. Okay? One is the straight line corresponds to the overall. So we ask the user to classify the quality in different moments that are, that from our point of view, were important moments in the transition going from S to R, and also the score session. What he think about the complete session during all the process. Okay, that's why that reflects the two straight lines. So obviously, as you can see here, in the case of the adaptation, the score from the point of view of the user, just only in this case, where he just pointed as as a 3.7, I think it's more or less, most of the time is very good. He's saying this from 1 is bad and 5 is okay or is excellent. So you can see each time the user say that it is very good the quality he's perceiving. Okay, in that case. Although, as you can see, we have variation in the loss, etc. And the overall performance, obviously, he said is basically 4, no? In some case. So it's very good from his point of view. Okay, just to conclude. So the idea is what we have tried to show here with this presentation, with this experiment we are doing, is that first, in general, adaptive applications are really interesting from the point of view of heterogeneous network, basically in wireless and mobile scenario, where you will have a high variability. The use of machine learning techniques, in this case, that try to model the user perspective, has been shown in this case that reflect very well what the users perceive about the system. And so the idea of this combination, the possibility of trying, not only because in this case we have based our learning process in previous examples of the user. Okay, so one of the issues, as you can see here as a future works, is that we want to have a reinforcement learning, a process that, okay, we start with the previous knowledge and then we try to adapt and learn during all the process. So the user in any moment can give us new feedback that we can include in our system to try to adapt, in this case, the learning process to the real behavior of the application in different scenarios. Okay? And the other issue is obviously try to not only work, in this case we're working with a global model for users in using a specific application, but the idea will be also to try to combine this information with user profiling. So the user also may have certain specific, because he has some problems or he wants certain kind of different specific condition. So to try to match both behavior in order to improve the quality of the application. Okay, thanks. Any comment?
Okay, again, room for, let's take 2 questions while the video people get busy putting up the video. Who has, and
interested, have you been able to try it with a number of different users?
Yeah.
And if so, how much variation is there between their preferences? Because I'm red-green colorblind, so I would expect that I would regard color to black and white as an early thing I was prepared to throw away.
What we generate is a global model of the user. That's why I was indicating that the next step is also to try to cope with this individual that maybe have a specific requirement in that case, and try to match both users. That's why also we understand that reinforcement would be good, because I can generate a general model. Okay, but now let's the application behave by your own vision of the profile. So it starts learning from your own requirement or specific needs, for example. Okay.
Have you looked at adapting on the basis of the content as well, even for the same user?
No, we haven't worked in that line, but this is something that also we, for example, because in one project we're involved, it's going to be considered. Yeah, I agree with you, and this is also interesting because that what you said. It's not in that case. It's just not all because you are using a specific application. It will be also because of depend on what you want to see or the application you want to use. You will have to adapt also. Yeah.
Okay, thank you again.
Thanks.
Now to the most exciting part of this presentation. Is it going to work, gentlemen? Okay, let me just start with introducing Philippe and hope for the best for the presentation. Philippe Ansett is network architect at the University of Tennessee in Knoxville, where he's now enjoying his early wake this morning. Philippe, I don't know all the wireless networks in the world, obviously, but with way over 1,000 access points in his network, I'm pretty sure it must be one of the, if not the largest wireless network in the world. But I think he has the right qualifications for managing that. He has a master's in zoology from the University of Brussels, which probably will come in very handy to deal with end users, and a master's in computer science at the University of Tennessee. Philippe, apart from running this network, also does all kinds of exciting, more cultural oriented things with wireless LANs, and so I'm very happy we have him here. Let's just hope that the next time it will be in person instead of via video conference. Philippe, if you're ready for it, then the floor is yours. We're not hearing anything, Philippe. It worked before.
I can dial it. I can dial it. Oh, there you go. Yes. Okay. So as I was saying, thank you, Klaas, for inviting me to your conference. I wish I was smelling those nice Mediterranean plants, but I'm in an air-conditioned room here in Tennessee. We do have a lot of interesting plants too. So we are on slide 1, which say an early adopter of full Wi-Fi coverage on campus. So is sound okay? Okay. Oh, there you go. I can see my slides. Can you redo that again? So that way I can sync mine with yours. Yes, there you go. Awesome. We are going to slide number 2, a brief introduction to the university. Do you have slide number 2? Next slide. There you go.
Sorry, it didn't work.
So 26,000 students, 4,000 faculty and staff. No, that's one too far. There you go. You may see the beautiful scenery of the campus. It's 200 years old, very young for a European standard, but nice buildings. They're pretty close to each other, so it's fairly convenient for wireless leaks between buildings. On the right-hand side, you see the far right yellow was our first yellow deployment, which was our phase 1, and the far yellow left is our agricultural campus. It was part of the first phase 1, and then the purple color is what we call the phase 2. Those were more athletic and services-based buildings that we covered later on once we felt comfortable with the deployment. Next slide, please. We created. Originally in 1999, we were testing, fooling around with access points, looking at web, signal assignment, channel assignment, and some vendor realized that we were quite interested, so they approached us, and we took advantage of a vendor competition between Lucent and Cisco to make them compete with each other, and finally they gave us actually 45 access points. We took advantage of these access points to create 8 pilot projects to see how the community would react to that network. Remember those days, the wireless access card, the wireless cards were pretty expensive. They were about $200 a pop, so really passionate people would join it only. And we had an immediate success. The business school required about 50 students to have laptops with wireless. The architecture students had Mac with built-in airport, and computer science, that was obvious. They actually were using wireless even before wireless existed. So then seeing this, the president, who was a friend of a Qualcomm executive who convinced him that wireless was the future, literally came to us and said, I want you to come up with a plan to put this whole university wireless in, and you have 3 days, or I ask an external contractor to do that. So we used the existing pilots to create a matrix of concentration by type of building. And based on that, we came up with an Excel spreadsheet and all the coverage, all the size of our buildings. We estimated that dorms included, we would need 1,500 access points. Today, we have 1,250, but we have not covered the dorms, so we are very close to our original estimate. And he also told us that we were supposed to have that done in 1 year, which was a pretty scary plan. So the pilots really helped us, and also at the time, Power over Ethernet was being released, and it literally saved us. That project was impossible without Power over Ethernet. So we really started in January 2001 because we had to do all the vendor decisions. And by March 2002, we could really claim that the main campus was completely wireless, not some other buildings. There you go, size of Nomad. So, as I said, we started fooling around with 5 APs. We had the 5 plus 45 of the donation for the pilots. At the end of 2001, we had the number of 1,000. We were really excited. And really now we keep adding access points, but we are at about 1,250 access points. And as Klaas mentioned, in an academic environment, it's probably one of the largest wireless networks. I think Canada, University of British Columbia, has 1,300, but we have to find 50 spots to put access points so that we can equal them. And actually, this is not a joke. We have so many building leaks that we really don't have to provide much outdoor coverage. Only on really wide open space do we provide outdoor coverage. It's, in some cases, I will mention that it's a problem of interference between buildings. Next slide, please. So I mentioned the project unthinkable without power over Ethernet, all the requirements of alternative current. Even though we use only 110 volts compared to 220, it was still unthinkable, the price-wise and time-wise. So how did we do also for the thinking? If you remember, 802.11b was ratified at the same time as 802.11a. Only radios at the time were not available for 802.11a. So we really believed that A was the future at the time. G was being discussed. And so we decided to go back to our physics books and see what it would take to put the access points, the density of access points, to actually be ready for 802.11a. And we came to the conclusion that if we provide 25 decibel at 2.4 gigahertz, it would extrapolate to 18 decibels at 5, which was still a very good throughput. I think it was the equivalent of 36 megabits per second, theoretical. So that's when we started our discussion with Lucent, who had that double bay design. It was literally a PC, a tiny little box with two slots where you could stick a B antenna and you could add an A antenna. So we made sure that the CPU would support that. And also, one little detail, the original design was PCMCIA, but PCMCIA only supports up to 12 megabits per second. And so we asked them if it would be card bus compliant, and they confirmed that. So we bought these access points. We still have those today, and so that's 3 years after the beginning of the project, and we are expecting to use those for another 2 to 3 years. So that's probably 6 years with the same hardware. We still pat ourselves on the back for that decision. Also, we decided to go with 4 channels instead of 3, even though it was the advised number by the IEEE. By measurements, we realized that 4 channels was as well working. The little loss, we had a loss of 5%, give us so much convenience in our deployment that it was not worth the trouble of going to 3 access points, 3 channels. Sorry. Next slide, please. When we picked, we did not do the deployment ourselves. We had to do 1,200 or so Cat5 drops within 1 year. We used the help of an external contractor. But we realized that the knowledge of campus was more important than actually wireless expertise. Also at the time, not too many contractors knew wireless, and the only existing ones were very expensive. So we decided that we will teach the contractor to do wireless survey, and we took a local one that actually knew the topology of campus very well. Then we did the survey of the survey. We had meetings with them to really see if their survey made sense. But regardless, you need to survey your survey constantly and go on the field. We use students for that. We also taught them scripting because they had to configure all these access points, and so we did some automation for them that revealed to be very useful. And power over Ethernet was so expensive at the time that we completely changed the structure of the way we lay down our cables. We asked them to completely centralize those cables within, of course, the specs of Category 5 cabling, which is 100 meters, but that saved us a bunch. Then we went to our acceptable usage policy, which made us literally become the owner of the 2.4 gigahertz and 5 gigahertz spectrum on campus. We said, if we provide wireless in a place, you will not interfere with us. And finally, this is access access is a key factor. Unlike regular network devices that are located in equipment rooms, access points are all over the campus. At the time, we didn't really consider that problem, but it's in all offices, in hidden offices, you need keys to every place. It's a true nightmare to access these access points. So remote management is definitely a big help. Next slide, please. When we did the survey, we also realized that the card we were using, at the time it was a Lucent card, was very sensitive. It was a high-quality card. So we made a calculation to see if it was worth to subsidize that card for students. You had the cheap cards that you could buy in the big supermarkets at the time, very cheap, but also the sensitivity was not the same. So the famous 25 dB that we were providing everywhere, in some cases, was literally a lack of connectivity for some users. So we decided to subsidize the cards 50%. So we would reach literally the same price. We would provide really high-quality cards for the same price as the cheap cards, but we saved so much in support that it was really worth it. Same antenna before and after. That seems trivial, but it was really. When you do your survey, you better stick to the kind of brand that you use when you are doing your survey. And also that we had some new buildings. Never do a survey of a building when it's empty. It's amazing what people can bring in buildings and completely change the coverage of these places. You literally have to completely redo the coverage after the fact, or just wait for people to populate the building. I mentioned that earlier. You do a survey of a building, you base that on a map. Usually when you do your survey, you go with one access point, you move it around the building. Building next door have not been yet deployed, but you realize that you assign a channel on one end of the building that's really close to the other end of the building, and you have more interference between buildings than you have inside the buildings. And also as humans, we tend to believe that vertical is harder than horizontal, but electromagnetic waves tend to believe differently. Mostly because ceilings, you only have a ceiling or two for 3 floors, but you have so many walls inside the same floor. It's amazing the difference of coverage. So vertical goes a lot further with wireless, except if you have really hardcore rebar floors. Thank you. How did we do as far as the network design? We realized that we needed to provide roaming. We believed immediately that students will have their telnet sessions open and would walk around, across campus with those, which is not really the case actually, but we like to believe it at the time. So we decided to provide roaming across the entire campus. So the main campus, if you remember the first slide, that big yellow zone, is one huge flat network. It took us a lot of time to convince my colleague to go back to those big, huge, flat networks because they were so pleased with switched and routers all over the places. But it's working. It worked. Of course, we had 1,200, let's say 1,000 access points, but only maybe 200 users at the time, so it was not a problem. And today, it's a bit different. But mostly it was for IP contention. If you think about it, we have some buildings that have maybe 20 PCs constantly connected on the wired subnet, but we have 5 or 6 classrooms. If those are heavily used classrooms for wireless, you may increase by an order of magnitude the amount of people that are joining that building for an hour. So how do you do your IP design? Yeah, VLAN is really the only way we found to solve that problem. So today we measure about 50 to 60 packets per second of broadcast traffic. It's okay. We still have decent download speed. Web and email are fine. But when it comes to voice over IP, I wouldn't say it works well, especially when you have those small phones. The CPU of those phones does not like to deal with 50 or 60 packets of broadcast. Laptops don't mind, but we will have to change that. So a few tricks briefly. Next slide. I'm sorry. Of course, we use private IPs for our APs. It provides security by obscurity. Also an ease an easy way to number those APs in that huge flat network. The funny one, we use pin cables. All network engineers hate pin cables. I don't know why. And it's very convenient for them not to unplug them when they go and connect regular users. We share the network with, we don't have a dedicated network for wireless. We also use a connection convention, which is we go from the end of the switch to the beginning as opposed to the wired port, which goes from the beginning of the switch to the end. And we hide APs in drop ceiling because the cards on the access points are the same as the cards on laptops, so we fear that people would really, they would get legs, so we didn't want that to happen. And we mark them on the ceiling with a very tiny sign. Next slide, please. So the original test, of course, it was wide open. Not too many people knew about wireless. Then we tried web. Even before web was discovered to be completely broken, we realized it was completely unmanageable. Everyone was sharing the same key and could sniff each other, so that was really useless. So we went between, we had to decide at the time between Leap from Cisco, the boxes, and the Lucent proprietary solution. I mean, both were proprietary. Lucent was using a combination of standard protocols that made it proprietary. They were using PPP to the access point and then Diffie-Hellman key exchange. It was really nice. It was completely authenticated, encrypted, just like 802.1x with EAP types is today. But it was really one company supporting these things. And at the time, Mac OS X and Windows XP came up, and they could not keep up with the OS. So we decided we would downgrade all the access points to just regular access points. We did that with scripting in 5 days. We did the whole campus. It was a pretty heavy week. Then we switched to what we have on campus, which people have to register their DHCP through a web portal going to LDAP. And we do the same on wireless, but on top of that, we silently monitor our ARP cache to see if anyone is spoofing IP address. If people have registered MAC address and spoof MAC address, then we cannot detect them, but we live with it. So our next move will be to go to 802.1x this summer with EAP TTLS. And because we plan to, we still support the older solution, we will provide SSID, type of security per SSID. And luckily, we have to actually upgrade those network cards in all access points. We will have students going all over campus to do that. And we get 802.11g for free because those new cards come with 802.11g. So I don't think anyone will complain about that. But we are convinced that 802.1x is not the one-shot solution. If you see on that picture, those are robots that have an iPack as the brain with wireless, and they run Linux for PDA. I don't think faculties will be really pleased if we tell them each time they run their 30 cooperative robots, they will have to type passwords for 802.1x. So we know we'll have to support this esoteric application. Next slide, please. So what do we see today? We see 8,000 MAC address registered. We see up to 1,200 concurrent users on an average day, which is usually between Tuesday and Thursday. People tend to not come on Mondays and Friday for some reasons. And 2,000 different MAC address will join on average. We'll see 2,000 different MAC address on a daily. And we have seen peak utilization of up to 1 gigabit per second if we sum all wireless interfaces. That's not on the gateway if we sum the gateway, we only reach 600 megabits per second, but you cannot exclude people talking to each other at layer 2. And about 2/3 of the users are students, so very, very trendy for them. Next slide, please. So what do we see as happenings? Rogue EP, we only see them appearing where service is not available. In dormitories, for instance, we have detected up to 40 rogue access points. So we have decided to provide minimal coverage in the dormitories, but they all have 100 megabit to the pillow. So, and those rooms are not that big. So I really don't understand why they want the wireless. The faculty who want to stop services during exams, that's a good one. We had to explain them that really the wireless network goes beyond their classroom. And we also have wireless ISP without consent. We have registered users aiming point-to-point wireless antennas from surrounding buildings to actually provide connectivity for their buddies in their rooms. And so we do hardcore monitoring per user and per access point, and on our graphs we tend to detect those, not easily I would say, but they show up. Next slide please. So the new Nomad, so originally it was designed for coverage, but we realized that really people don't move too much with their laptops. They move within the buildings, but they don't tend to walk with a laptop in their hand. So we are now adapting to density. We see literally hundreds of laptops in classrooms, and it's becoming a throughput problem. People are sometimes complaining about. And faculty, imagine a faculty saying, like, and now everyone download my huge PDF slides. You have 200 students downloading on those poor 4 access points. I don't know, 1 megabyte slides at the same time. So we have to also teach them to sort of stagger those requests. But we are convinced that 802.11a is not dead, and it will definitely be very helpful in line of sight situation for those classrooms. We actually request students to get ABG cards so that they can adapt to the new environments. And we know that we'll have to purify our wireless network because it does not work for voice over Wi-Fi. We have tested that on PC. We have tested that with Spectralink phones. The connectivity is not great. We will have to probably divide our large wireless subnet and definitely filter verbose protocols, and probably do quarantine of those SASR infected people. Next slide, please. So what happened? Originally, wireless LAN was supposed to be a complement to LAN and not really a replacement. What we see is that by population, it tends to be a replacement, but for some people, LAN is still the decide. If they have a desktop, they stick to the LAN network. You cannot exclude that faculties are requesting their students to use laptops. In many grad students, those people are mobile, so they want a mobile device. The School of Business this year, you cannot join the School of Business if you don't have a laptop, 2 batteries, and now they require an ABG chart. It's pretty hard on their budget, but these people are hardcore on the wireless. Same for the School of Architecture and some of the engineering school. So the instructor, actually, it's not that they just want those laptops for convenience. They are definitely adapting using some applications that they will request students. In some of these auditoriums, the screen is not big enough, so they will request students to be interactive. They do polling. They say, did you understand what I just explained? So you have new software showing up. Actually, one is Silicon Choke, and these guys are literally using broadcast to push slides to the instructor. So imagine that's a nice networking nightmare there, because those slides are being pushed basically to the 950 access points. And fortunately, the vendor is pretty good at working with us, so they have enabled it with multicast. So now we have to turn every single wireless access point port into a multicast port. But that doesn't still solve the problem of the fact that access points are not multicast enabled themselves. So we'll have to work with that. Those are definitely challenges. Online exams, that's a pretty good one, because you immediately see people using instant messenger to exchange answers. So we have developed a few technologies. Like one day I went in a classroom and the instructor presented me as the wireless engineer that would sniff everything they were doing. Luckily, within 5 minutes, a guy was infected with SASR, and I detected him. I went in the classroom and said, like, who is Joe Blow? He looked at me, panicked, and by that time I think everyone shut down their instant messenger because they really thought I was able to sniff everyone, which everyone knows it's impossible, but don't tell the students, please. Actually, that silicon choke application is one of these applications that literally takes over the laptop, and the TCP/IP stack. So instructor could literally request these students during exams not to be able to go anywhere else but to the exam website. So that might be one of the help. We'll see how. I thought the instructor, you should adapt your question to the new style of examination, but I don't know, they like that too much. Next slide, please.
You've 2 minutes left, Philippe.
Oh, 3 minutes over, so I'll be fast. So that's the Klaas was talking about those esoteric applications that we work on. We designed one that's used basically location awareness over Wi-Fi. It does not require any hardware, no ownership of the infrastructure. If you go in your city and you see a bunch of access points, you can see the MAC address and the signal strength, which we can do it with a few cards with our software. You have to basically find a map. Do a fingerprinting. Triangulation does not work for Wi-Fi, or it does not work well, because as soon as you have a wall, if you want to extrapolate distance to signal strength, it doesn't work well. So what we did fingerprinting. We do a survey. Basically the idea of can you hear me now for a bunch of points on the floor. We convert those XY coordinates. We take 3 GPS locations outside the building, and we convert XY floor into real longitude, latitude. I will let you really go read that. I have a pointer on a website so that you can read the design of it. But it's really nice because you can store geographically the information geographically. So artists can use it, engineer can use it, historian can use it, anyone can use it. You can store a picture at a location, and I think it would be a great complement to those distributed storage initiatives, so that you can store across distributed storage devices images and tags and insults if you want. Next page, please. So so all you need is a software. You end up with, depending of the type of building or the quality of the survey, the number of points that you survey, you end up with between 1 meter in the best case to 6 meters. And I would have to be honest, sometimes we did have very nasty places where we had 15 meters accuracy. So that's almost, to the access point level. And but it changed, and we are also changing our algorithmic. We are using Bayesian algorithm. We will use Bayesian algorithm to increase the accuracy of the survey. So also, if you use different wireless cards, it will be a problem. But we devised a few protocols where, like if you remember the Palm Pilot, you had to go on 5 different spots on your screen to synchronize the screen. We will request users to go to 5 known spots to basically calibrate their radio cards. So if you want to write the website, that's where you can read more about the design, and later on we will have our own website. Next slide, please. So, but one of the applications, we designed a geomapper. So that's the survey tool. We found out that it was very useful to do survey. And then because of new access points are now reporting in traps, they are reporting when they see rogue access points. We can actually convert every access point into a mini client and use the fingerprinting that we have to locate, to provide the location of the rogue access point. That's one step beyond the fact that otherwise access point will tell you, oh, there is a rogue access point in the neighborhood of this access point. Well, some access points have a pretty good coverage, so you may end up spending half of your day just looking for the access point. So we are definitely planning to use the survey tool with those traps that we receive from new access points and map that to provide a location. And if you think about in general, the coverage of Wi-Fi networks is useful for many, many things. And so thank you for listening to the presentation. I'd like to remind you that because it was a flat network, it was really easy for us to turn it to a huge IPv6 domain. And so anyone can enjoy an IPv6 on a wireless network these days.
Thank you, Philippe. Normally you would have said we have to stop now. We don't have time for questions and catch him outside. But given the fact that that would be hard, I would like to see if there are a couple of questions and have them answered. Here is a question coming from the largest hotspot in Europe. Sander?
Yes, it's UT as well, I believe.
Yeah. Correct.
I'm Sander Smit from the University of Twente. How this guest can access your network?
Oh yes, it was one of the slides. So the way we do is we do it by proxy trust. You have to know someone at UT, and anyone can register someone else's MAC address. So basically, the person will come with their laptop. They will pop a web browser. It will prompt for user and password. You have to find someone that trusts you. They will enter the username and password, and your MAC address will be registered forever until the user remove it from the entry. And also every year we clean those entries and we request people to re-register. Does that answer your question?
Yes. It is also amazing to see that your networks like our network. The same philosophy, TTLS, 8.21x, and also different color cables on the same location.
Yes, so I think we will join the Roam EDU for the 1x, so that way it will solve. But unfortunately, that will only allow Europeans to come to Tennessee, though.
Well, we saw the picture. It looks pleasant.
Okay, yeah, you're welcome to join. I will sponsor you if you don't have 1x enabled.
I have not a question. Do you also connect to EduRoam?
Will you going to be part of EduRoam?
I'm sorry, the question got disconnected. Could you repeat, please?
Will you be connected to the EduRoam hierarchy that is now being built in Europe?
Yeah, I'm a firm believer that it's an awesome solution for NRANs and education networks, and I think they should even move beyond and connect the T-Mobile networks to those kind of initiatives. You know, right. Just like a gigantic DNS domain. I will push for that, and I'm already pushing in the US. Okay,
thank you once again, Philippe. I really want to recommend you to take a look at this Wi-Fi initiative. It was very funny. I took a look at it and discovered graffiti in front of my own house on the site, which is in Utrecht in the center of the Netherlands. So it's really spread out nicely over the globe already. I also, apart from thanking Philippe again, I would like to have a hand for the video people who have been working very hard the last hour to make this possible. Thank you, and see you next year in another mobility session. I think then we have to move for the main hall. Thank you.
Thank you. See you in Poland.
Okay, that's a deal.
I will come physically this time.
Licia says you said the same last time.
What did you say?
Licia is saying you said the same thing last time and you're not here.
Yes, but this time I will budget it ahead of time.
Okay, thanks. Bye-bye.
Bye-bye.